So our next presenter is Olaf Faaland from the Lawrence Livermore National Laboratory. And he's going to talk to us about how to safely deal with ZFS in a clustered environment. And more likely about how do you safely import a pool in a clustered environment and not corrupt it by importing it on several nodes at the same time. All right, please welcome Olaf.
Hi. So, okay. So you heard the problem already. You have a clustered environment. You've got shared storage, and you want to make sure that you don't accidentally import the pool on two nodes at the same time. ZFS won't notice that this has happened. Both nodes will start writing Uber blocks, and you'll lose your entire pool. So we've written MMP to reduce the risk of this happening, and it's merged in ZFS on Linux. It's reasonable to ask why, excuse me, why do it in ZFS, and why ZFS doesn't prevent this already. The two mechanisms it has, the namespace check when you perform the import is local to the node, and the host ID must be disabled with the force option in the on the failover node because the pool was definitely just imported on the other node, and the whole reason that you're importing is because that node's presumably down. However, maybe it's not really down. We've had cases where we have an external, we have an external system, an AHA system, that attempts to make sure that these two systems can't import the pool at the same time. In our case, they're typically work with power control. So they're supposed to detect that host A is down, power it off, and then start services on host B. But we've had cases where the HA system was misconfigured, and we've had cases where the power control system that the HA system depended on lied. So we started working on this using a design that was written by Richard Correa back in the day. And found it's partially an issue of my learning curve, but also just found that it was too complicated for us to get done quickly, and that there were issues that made it more complicated than it needed to be. And so we took a step back and said, okay, what do we really care about? The main thing is try not to disrupt the way people use ZFS already. Try and make it as safe as possible so that it's difficult to misconfigure. Make sure that we can test it viably in our automated test system so that if we break it, we know. And simplify it enough that we can get it done and merged. So a big consideration is, if you're going to do this, is where do you look? How does host B know that the pool is imported somewhere else? We wanted to keep it simple, so we, among other things, we chose to use the disks themselves. So on the disks, or the devices themselves, on the devices, we've got our map here of where ZFS keeps its data. We thought about just about everywhere. The blocks in the pool aren't a good choice because you have to import the pool to find them. And even if you import the pool read-only, that's actually it's not reliable. You can't, we'll talk about it more later. We looked at stealing space from the boot block or the boot header or the blank space at the beginning of the of a label, but we're concerned about interfering with someone else who is also trying to steal unused space. We considered the NV list, the name value pair list that contains the configuration, but it's stored packed on disk, for one thing, and it's more than a sector in size. And so you can't guarantee that if you read it, you're going to get one whole NV pair or NV list. You might well get parts of more than one because it's being overwritten at the same time you're reading it. And as had been observed by, I think, probably many people before I even came to this, the Uber blocks being written to the Uber block slots already provide an indication of activity. So why not use this free capability that's already there? One of the issues that comes up with that is, well, okay, what if there's no activity in the pool? If it's quiet, Uber blocks don't get written. And what's more, they get written on devices where there's dirty data, typically. So you need something that's that you can count on even in those circumstances. So what we decided to do was to choose one of those slots and dedicate it to MMP. The rest of the Uber blocks slots are used in exactly the same way that they were already. When the sync goes to write a slot, it just chooses the next slot, wrapping around, but it skips that one at the end, and the one at the end we use to write to indicate activity even when the pool is quiet. This is just what I just discussed. So another question is, what do we put there? We considered a different structure than an Uber block, at least for that MMP dedicated slot. It could really be anything. But there were a couple of advantages to extending the Uber block structure. One is that then we could add MMP information to all of the Uber blocks that are written. And so when the import occurs and the portion of the import fetches the newest or best Uber block, it'll have useful MMP information for us. So we get some information without having to go look some special place for it. Another advantage is that it doesn't introduce a compatibility problem. We don't have to worry about you move a pool from a machine that's used for failover purposes. You move it to some non-shared storage where you don't need this feature anymore. It's just an Uber block, and there's no issue of compatibility and confusing it. In particular, if we write valid Uber block information there. So we added, we used the timestamp that's already there. This gives us 1 second resolution. And we don't really care what time it is. We just look to see if it changed. And then we added 3 fields at the bottom: magic, delay, and sequence. Magic is to tell us whether or not there's valid MMP information here at the end of the struct. For example, if the pool is brought over from a machine that has a ZFS that doesn't understand MMP, then we ignore those fields. Delay is the average time between MMP writes, which I'll go into in a little more detail. And the sequence at the moment is unused, but it would allow us to provide sub-second resolution on a quiet pool, sub-second evidence of changes. So I'll briefly go over how the import works. This is specific to Linux in one way, at least, which is that Linux always gets a config from user space. That's, as I understand it, not true in Lumos, and there may be other things that are not true as well. So on Linux, user space utility searches the disks looking for labels and assembles a partial configuration. It's partial because it doesn't have, I can't remember if it's log devices or cache devices, but one of them doesn't have a label with enough information to know what pool it goes to. And spares, I think, yeah. So it assembles this partial config, and then it issues a try import. Try import ioctl is used to get information about the pool. So if you issue a zpool import without giving the all or the pool name, find out the status of the pool, or just get a list of what pools are available. Try import is what provides that information. So the utility passes the partial config in, and the first, well, almost the first thing that the try import does is search all the labels of those devices, reads all the Uber blocks, slots, and finds the best one, meaning the one with the highest transaction group and the latest timestamp. It then uses the block pointer from that Uber block to load the MOS, get the config. It reconciles the MOS config with the partial one that it was given. It checks other information like features, and then passes back a full config if it was able to assemble one, and information about the import and whatever may have failed or and user space then takes that full config, passes it back in with an import ioctl, along with any flags like the force flag to ignore the host list. Almost all, or a whole lot of that work that the try import did gets done again. And the import either succeeds or fails, possibly after having rolled back. It then passes back status information to user space, which reports its results. So what I'm going to do now is go through how we arrived at the implementation that we ended up merging, starting with the initial idea was, well, we've got these Uber blocks on disk that already provide an indicator. So what we'll do is we'll just issue the try import repeatedly for some polling period and look for change. And if we see change within that polling period, then we know that we can't import safely. If we see no change, we'll assume that we can safely continue on with the import process. So that was try number one. We added that code to the user space utility, and we added an MMP thread in the kernel that would just write on a fixed schedule to that one dedicated MMP block, choosing one randomly. So the first problem we ran into is that that try import sometimes panicked the node. And it would panic the node because the import code first tries to load the MOS so that it can get the MOS config, and the root block pointer that it got from that best Uber block may have DVAs that refer to devices that don't exist if the configuration is changing. So that's kind of a bummer. And we found that going past that, even if you survive that step, again, if the pool configuration is changing, later on, the MOS config and that partial config that user space assembled get reconciled. And that code is more brittle than it probably needs to be. Well, some of it's definitely more brittle than it needs to be. But at that point, we said, okay, well, there's a fundamental problem we can't fix, even if we made the code less brittle. Maybe we should just try and avoid this problem at all. Instead of polling by repeatedly issuing the try import ioctl from user space, let's poll within the ioctl itself. We'll just repeatedly fetch the best Uber block, for whatever the polling period is. And if that doesn't change, then we can proceed. If we see change, then we bail out. We don't do the rest of the import process. So that helped a lot. Now the node doesn't panic. There's the problem of perhaps there's a delay between the try-import iocto being issued and the import iocto. The try-import may have concluded that it's safe to import the pool, but now the node is busy or something happens, and by the time it actually issues the import iocto, the pool's been imported on another host and it's not safe anymore. So now we do the poll within both the try-import and the import, which was fine because they actually go through the same code path. But now we have to wait twice as long. So we decided we'll pass the transaction group and timestamp that we found when we polled back. If we concluded there's no activity, we say this transaction group and this timestamp are the last one we saw, and it should be safe. And then when the user space issues the import octal, it passes those values back in, and the import looks to see, well, have the TXG and timestamp changed? If they haven't changed, then the activity test is still valid. So then it can continue and perform the import. Now up at this point, this polling period and how often those MMP blocks are written was based on settings or maybe even hard-coded in the code. Hard-coded in the code maybe would be okay because at least it's the same everywhere, but then the user gets no control, which is sucky. And settings is bad because maybe you've got host A is told to wait for 10 seconds and host B is told to wait for 1 second. Or rather, host A is told to wait for 1 second, to write every 10 seconds, and host B is told to wait for 1 second. So that the wait isn't long enough because you've set settings poorly. So we added the field to the can't remember what it's called, but the field that records the time between writes that I showed you that's at the end of the Uber block. And so now, not only does that record essentially what the user setting was, but if there's some delay in the I/O pipeline that's causing these MMP writes not to get to disk on the fixed schedule, which is ideal, host B knows that. So if for some reason the MMP writes are only landing once every 10 seconds because there's something gone badly wrong, host B knows that it has to wait a lot more than 10 seconds, and it can calculate an appropriate polling period. Another potential problem is that there are more than 2 hosts involved, and 2 hosts both try and import the pool at the same time. So we add a small random additional time to the calculation. So we've got the time that's based on the average period between writes, and then we've got this random term. One of the nodes will win, hopefully, and the other nodes will see activity because the node that finished first will write an MMP block, and they'll see that change. Now, we also don't want to penalize people that don't have shared storage or don't need failover. Why wait some amount of time for your import? So we added a property, multi-host. On means we want activity checks, and off means we don't. But you can't check properties without importing the pool because they're stored in the pool. However, it's okay because we've got those MMP fields at the end of the Uber block structure. So we zero them if the property's off, we set them if the property's on, and the importing host B, can tell from the Uber block whether or not MMP is required. So that's ultimately what we arrived at. These, by the way, these frequencies that I have here, I realized are wrong. So I'll give the corrected slide to Matt for posting. But we added a couple of, I think they're module parameters. One is the multi-host interval. That's how many milliseconds should go by during which every VDEV should get one MMP write. And that's so that the idea was that that's easy to understand. Every device should get a write, and so every device is providing protection to the pool. And then we just invert that to turn it into a frequency. The other issue that we address with a module parameter is to try and detect when the protection isn't working because the MMP writes are failing. So we keep track of how long it's been since one succeeded, and if it's been too long, we suspend the pool. Too long is defined as that MMP write interval times the number of failures that the user is willing to tolerate. And I think we have it set by default to 10, but that's something that they can change. Again, we got a lot of this for free just because ZFS already had the code to fetch the, quote, best Uber block. Best meaning the one with the newest information. And so for those MMP blocks, we just use whatever the most recently synced Uber block information was, transaction group, block pointer, and so on, and we just update the timestamp. So that gets to be the newest one if the pool is quiet and the activity is evident. Like I said, a really important thing for us was being able to test it, and in particular being able to automate the test. Importing two nodes on the same, or importing two pools on the same node is pretty hard because the first thing that ZFS does is check to see if there's already a pool with that GUID or name imported. The host ID is obviously, there's only one host ID. What we did was we used ztest. We run ztest. It's got its own namespace. It's running in user space. It's easy to tell it what host ID to use. And so now we have what looks like an active pool, files or loopback devices or whatever. And we can then try and import that through the kernel. And if MMP is working, it'll detect the activity and it will fail. We did have to modify ztest a little bit to skip some tests. It does things like stops activity in the pool and runs EDB to check that there's no space map leakage, and that sort of thing would disrupt the test. So we had a flag to prevent that sort of activity. There are important limitations. The biggest one is just that if there's something gone badly wrong in the I/O pipeline that introduces long delays but doesn't prevent writes from landing eventually, then that defeats MMP because it's depending on seeing no activity for some period of time. But you can't wait forever, so we pick an amount of time. So in our case, this is used in conjunction with an HA system that powers off nodes and provides us with a second line of defense. Other lesser issues are that there's no ongoing check. So once the pool's imported, we don't check to see if something's changing out from underneath us. but that could certainly be done, and it would be, I think, a big improvement. At the moment, if the pool is suspended, there's no protection when it's resumed. We don't check to make sure that nothing changed. We actually took a stab at that. There were minor complications, nothing that couldn't be worked around, but we ran out of time basically to get it merged. So that's something that I anticipate we'll add. When you MMP at the moment doesn't offer any protection if you're changing the structure of the pool in such a way that you try and add the same device to two different pools by doing it on two different nodes, or remove a. Well, yeah. It's not a big window in the sense that when you add a device, a label gets written, but these operations all check for a label before they begin their work. But you can use a force option that'll tell them not to look for that or to ignore it. And in any case, if you had an empty device and you add it to two pools at the same time on two different nodes, that wouldn't be detected. So that could be improved. And then we also didn't do anything to prevent someone from hosing themselves with zpool label clear, which we could do. So that's it. Questions?
So why don't you add the MMP magic rather than buffing the UB version?
Oh, right, sorry, thanks. The question is, why did we add UBmagic instead of just adding a feature flag or bumping the version, essentially? And the main reason was that we were trying to make it easy for someone to go back and forth between an MMP compatible implementation and not MMP compatible implementation if they need to do that. And also because it made our life a little easier, because then we didn't have to try and write code to help people handle that transition.
Is this strictly SASbased? And you mentioned more than two hosts. What would that look like?
The question was, is this SASbased, and what would it look like if more than two hosts are involved? I don't think it needs to be SASbased at all, or I should say no, it's not. That happens to be our environment, so maybe that's the example I gave. But ZFS is just looking at the devices on disk without regards to how they're connected, just with regards to their content. As far as multiple hosts, just as an example, we have servers where 4 hosts are sharing the same storage, and in our particular configuration, all 4 of those hosts aren't intended to import the same pools. We actually have pairs of 2, but it's only a few keystrokes away. And one can imagine that maybe there would be situations where you actually would have more than a pair. But it should work equally well with n hosts, at least for some small number. I haven't thought about limitations.
Did you consider having it such that when you enable multi-host, the property that it implies fail mode equal panic to avoid like the suspended pool case?
So the question was, did we consider enabling multi-host basically change fail mode to panic so that we didn't have to worry about the suspend case that I described? We did. Our thinking was that we felt like we didn't want to take away control if we didn't have to. And especially because that suspend case is something that we really, even though we haven't addressed it, it doesn't seem like there's anything fundamental that would prevent us from doing so. It seemed unnecessary to take that control away. But you're right, that would mitigate the problem. absolutely.
I have a couple of quick questions. The first one is, in your Uber block, you use delay, UB delay, I think you called it, and that was the average delay of writes to disk, I guess. Is there a reason that we wouldn't want to use maximum instead, or like the longest write to disk?
Okay. So the question was for the UB MMP delay field that represents the amount of time between MMP writes. I described it as an average, and the question is, why is it not the longest time? I agree with you, and in fact, it's not really quite the average. So I actually should probably change that in the slide too. So it's a rolling average if it's going down. If there's a long delay, that value is set to the longer delay. So let me rephrase that. When an MMP write succeeds, we go look at how long it took, because we recorded in the VDEV the time that we issued the write, so we can do the subtraction to see how long it took. Then we go look and see what the current value of that average is for the pool. And if this new delay is greater than the existing average, then the existing average value is just made this new delay. So if we have some long delay, some sudden long delay, then that MMP delay value is now the longest, this new long period. If it's less than the existing MMP delay, then we use a decaying average, 127 times the existing value plus 1 times the new value, so that it decays slowly over time. And if you're getting bumpy values, it will at least eventually go down.
Sorry, I had a couple other questions. One was, so I noticed, so you said that try import and then import do a lot of the same work.
They do.
We've looked into deploying, some kind of high availability like stuff at our company, but one of the big problems there is that import time is too long to pretend that it's true high availability. Do you think that there's some work that can be done there to lower this, or you said that you're using high availability software? Could you talk a little bit about that, I guess?
So I think basically the question boils down to, can this be made fast? The time that you have to wait, is that reasonable?
Yeah.
Okay. Yeah, we did think about that. So there are a couple of limitations. For a quiet pool, the activity signal that you're seeing are the MMP writes that are being written by that by the MMP thread that are on some fixed schedule. And at the moment, the smallest you can go as far as detecting that change is 1 second, because we're using the UberBlock timestamp field as UberBlock timestamp field and the TXG as the two elements that we look for change in. And the TXG doesn't change in a quiet pool, and the timestamp changes only once a second. But the MMP sequence field that we added, but we haven't used yet, could be just incremented every time we perform an MMP write, and so then you get to control how often those happen, and you could have much smaller periods where you can detect change. And even in a pool that's maybe not quiet, but where the activity isn't, where it's not being slammed, maybe those MMP writes would happen in a higher frequency than the syncs do, depending on how, what the workload is. However, there's that ugly problem about delays in the I/O subsystem, and I've only personally been doing work involved with file systems for about 3 years, but I know a lot of you have been doing it for a lot longer than that, and I understand that bad things can happen, resulting in very long delays. Machines that are just horribly bogged down and, swapping like crazy, and interrupts firing like nobody's business, and now every write takes an eternity to get to disk. And that kind of thing is problematic because we're depending on that polling and looking for activity. You can get fooled. How often that sort of thing happens and what takes to make it happen, I'm not a very good person to ask, but I suspect there are a lot of people in this room that are.
Yeah, so I'm guessing if you use like this in conjunction to other mechanisms for high availability, the end result is you're trying to improve sort of the reliability of clustering. And you can use also, I guess, disk reservation, SAS reservation, things like that. So like at the end of the day, I think you're not trying to like solve it 100%, but just to make it much better, right?
Yeah, so the question statement was just, well, there are other mechanisms like SAS reservations and disk reservations that allow you better or give you other mechanisms to provide protection, and this is just one that adds to the options and hopefully the overall of it reliability. So yes.
I was just wondering, since you need to rely on wall times as you're going between multiple systems, how do you deal with the fact that wall time isn't monotonic?
I don't rely on wall time.
You said it was using wall time stamps in all of the activity logs.
So we're looking for change in the value. We're not looking to.
You said you store the per second timestamps, and that's what, and you're looking for one of the highest ones when determining the best Uber block, and those were based on wall time.
And also,
Oh, I'm sorry.
you and like you've got the same second going on for seconds.
Okay.
Yeah, that's probably what I described. Like the classic leap second dispersal bug, where a second now lasts a lot longer, so systems don't see
Right.
760.
That's a good point. Okay. That's a very good point. So I would say that if we got off our butts and started putting the value in that MMP sequence field, that would address that problem. Because we don't look to see that these numbers have increased. We just look to see that anything changed at all. And the intent of the MMP sequence is that we would be stuffing a monotonic value in there. The ticks or whatever, whatever timer is available for the system, in our case, Linux.
Are you also, I thought that you were also looking at the TXG in the Uber block.
Yes, sorry, that's correct. We are looking at the TXG, so even if the seconds don't change, if there are transaction groups syncing, which obviously are monotonic, then we're protected. Thank you. That's correct.
It's kind of like the timestamp is like an extra check. Even if you got it imported on two systems, they might be writing the same TXG, but they would have different timestamps. Is that the idea? It seems like the TXG alone is enough.
So
It's 1 second wall time, so they actually probably most likely have the exact same value.
So the timestamp so the TXG provides us with an activity indicator when the pool is busy, and the timestamp provides us with an activity indicator when the pool is not busy. But you're correct; it's not monotonic, and so we should actually use the sequence number field so that that's closed. Yes. Sorry.
It sounds like you use this in conjunction with a lot of other mechanisms. This is a desperate last attempt. Obviously, there are a lot of holes in it because it is a last attempt. Do you, presumably, any attempt to import the pool that fails because the thing that you think is dead just wrote to it, do you take an action? To me, you want to take a pretty drastic action. You want to blow your own brains out because clearly the system is in a very, very screwed up state. What steps do you take under that, and have you seen that in practice?
So the question was, given that this doesn't handle all cases and is intended as sort of protection, as last-ditch protection, how do we handle it in our systems if MMP detects that another system is actively has the pool imported when we don't expect that to be the case. Like, for example, do we power ourselves off or something? And the answer is basically yes. We use Pacemaker, and so and it's configured so that if it checks if an operation fails, an import, for example, although this applies to other operations, it's configured to power off the node where the operation failed, and then attempt it on a failover partner. And in our case, it powers them off. It doesn't power them back on again. It could be configured to do so. So that's how we attempt to address that. We don't panic from the node itself on the theory that we don't need to. We just failed the import. But it's a good point. It's not perfect, and you could certainly do that.
And have you seen MMP protected takeover in practice?
No, we've only seen it in testing. And in our case, it actually protects us in two different scenarios, really. One is the failover scenario that we've been talking about, with where our HA system is really the primary line of defense, and MMP is a backup. But the other place where it protects us, where MMP is actually the main line of defense, is that we've got these clusters. For example, we have one network file system. It's got 52 nodes. Those are all pairs, so that's 26 pairs of nodes that are sharing storage. And we use a tool called pdish to run a command across all of those 52 nodes at the same time, because we want them to be the same. But, pdish zpool import -a would be really bad. And in that case, it's some human admin typing this while he's doing maintenance. And there's no HA system to protect him or her. So that's the other place where this protects us. Looks like we're done. Thank you. Oh. Lots of really helpful people. I wrote a lot of code, but a lot of other people did too. And thank you.